Right. So we're basically moving on to a new topic in a sense on the module three. Right. I believe the last topic that we looked at was related to thermal properties that would encompass specific heat capacity, latent heat of fusion, vaporization, heat capacity, all of those lovely things. We looked at different experiments, method of mixtures, method of electrical methods that you can use to find the specific heat capacity of different stuff. We ought to pay attention to those things. We must know what is taking place whenever you see those types of questions, or be able to can help yourself with those things, right? I think the information has been posted already as it pertains to that. Now we move on. We want to finish the syllabus, right? And we want to be able to can review things in short order, right? So we move on to what we call heat transfer, right? So a part of this lesson, we are going to speak on the three methods that we use in physics whenever our that we talk about whenever we're dealing with heat transfer. And I mean, when something is being transferred, it's just moving from one point to another point. And the three main ways heat is transferred is through conduction, convection, and radiation. And what we're going to do today is to see how these things can apply in physics, right? To find out certain information, you know, and the list continues, right? So we're going to move on to the first one that speaks to thermal conduction, right? Now, conduction, of course, right, is that process by which heat flows from a hotter region of a substance to a cooler region, right? Without there being a net movement of the substance itself, right? So that is what is happening whenever conduction is taking place, right? And it generally happens in solids, right? I mean, not every solid is able to conduct properly, but at the end of the day, it is one that that generally happens in solid, right? And we're seeing that it describes it to say that it is that flow of heat from a hotter region to a cooler region without the net movement of the particles. So what you essentially see happening is just vibration taking place. So at the hotter end of the system, give me a second here. I'm trying to find at the hotter end of the system, what you would observe is that the particles would vibrate more rapidly, and of course, because it's vibrating, it's going to cause the neighboring particles to vibrate as such as well, right? So that is what is happening whenever conduction is taking place. So if you heat a piece of metal, right, what you're essentially doing is that on the hotter end, you're causing those molecules to vibrate, and in turn, it will cause the other things here to eventually vibrate. But not only that, in metals, mainly, you have free electrons that are able to move about inside of the structure, right? So by way of increasing the temperature, you now give those electrons more ability to move along the metal. And that is how we describe conduction. All right? Are we good so far?
Yes, sir.
All right. We ought to be able to kind of draw a little bit of diagram sometimes to just start to explain this. So even this simple diagram here, you can get your marks from this. You don't even have to write a statement sometimes if they ask you to describe or to talk about thermal conduction. If you can just remember particles vibrating, you just annotate the diagram and show that the energy is flowing from a hotter region to a cooler region. You can get some marks, right? If you don't know how to put it in words. Cool? But know these information, you know, of course, it's very important for us to have that knowledge in our back of our heads. All right. So we know already that metals are good conductors, right? Whereas non-metals are generally poor conductors of heat, right? But why is it so? Now, based on my slide here, it says that the answer really lies within the atomic structure of these materials. If we look back on our periodic table, right, well, you would see your metals, your non-metals, and other stuff, right? With a metal, right, you realize that you have um, free electrons that are able to be to be knocked off the shell, or in a sense, metals on a whole um, give away electrons, right? When it comes down to non-metals, more specifically group 4 elements, they don't give away electrons. They only share electrons for the most part. So those are some of the specific reasons why you would have a metal being a good conductor, because it has free electrons that are easily, readily available to be given off. Do you understand? Right? Versus no a non-metal which don't give away electrons. It only accepts electrons. Right? So that is where the answer really lies. You understand? So when you heat up a piece of metal, right, you see where those particles or those electrons will easily get excited and vibrate, you know, from one point to another point. Now, this diagram that you're seeing at the top of the screen here, it's a very important diagram, right? I'm gonna look at it further in the next slide. But what really happens is the fact that once you have a conductor, right, there are two types of bands that any material has. It has a valence band and it has a conduction band. Now, when it comes down to the metals, what you see is that the valence band and the conduction band, they're connected to each other. So this now, when the electrons in the valence band, and the valence band just speaks to the outer shell, right, of the atom, when those electrons are excited, cool, what you will see is that there will not be a delay in the process of transferring the electrons because of the fact that the conduction band is literally on the valence band. You understand? So that is what is happening in a general conductor, right? Let me know if you have any questions. All right. Now, this is a diagram now that sort of explains all of the what would I call it now? The whole thing on the different types of I would say elements in a sense, right? So you know that we have metals, we have group 4 elements will be semiconductors. They're neither good conductors nor good um, good insulators for the most part. We could even reverse it to say that they're sort of like a good conductor and also a good insulator at the same time. So there are two ways we can look at a semiconductor. Um, when we look at insulators on a whole, like, you know, a more like of a group 5 element and all of that, all right? Those elements, this is how the gaps, the band gap, well, not the band gap, but this is how it looks in a sense when you're looking at those elements, you know, from an atomic level, right? So we said that every element will have two types of band. It's gonna have a valence band. The valence band just speaks to what is happening on the outer shell, right, of the atom, right? And of course, the conduction band is what happens when those electrons are excited, right? Now, when you look at the metal again, this is the same diagram as what I would have shown you just now, right? The valence band and the conduction band, they're on the same level, so to speak. So as soon as we excite our electrons, right, from the valence band, they quickly move across the conduction band, and then and I mean the result of that would be, you know, the metal would conduct easily. As it pertains to semiconductors, as you can see here, there's a gap in between the semiconductor material, and what we're seeing here, this is what aids in the process of using semiconductors to sort of like, allow electricity to flow, right, to some degree. So what we're essentially doing is that if I were supposed to apply some heat to this section here, right, what would happen is that these electrons would become excited, of course, and if they gain enough energy, then they will jump across the gap, which we call the band gap. And by jumping across the band gap, that will now enable it to conduct. This is going to become more useful to you when you study further physics about semiconductor devices, right? It's going to become more useful for you, but you just need to understand that it is because of the small gap that exists between the conduction band and the valence band. That is what allows it to be able to can conduct. You understand? Now, when it comes down to a pure insulator, right, we're seeing here that the gap between the valence band and the conduction band is much greater. So that is now the reason why, a piece of rubber, for the most part, does not conduct electricity or does not transfer heat easily, because of the fact that these electrons would need too much energy, you understand, for it to reach to that level. Mind you, insulators can conduct, and I've seen it for myself. Like, my time, I don't even know if some of those things are insulators. Like, sometimes you will get like a plastic spoon or some type of so-called spoon that you can put in the pot, those rubber spoons or something like that, and it actually get hot, And also I've seen where rubber actually can also shock you too. So I mean, it just goes to show that sometimes, either these materials are not completely insulators, right? Because of the fact that they might use other materials to make it up, but or it could be a case where the electrons gain enough energy so that they could jump over to the conduction band so that they can conduct. Because there are some pots, sometimes they have these handles that you think that is insulated, but you if you're crazy enough to go and hold on to that, it will burn you. You understand? So that probably could just explain what is happening there. Those electrons gain enough energy to transfer to the conduction band, right? Okay, are we good so far? Let me know if you're having any issues with hearing me. Like if I'm breaking up or not like that nature. All right, good. Okay. Now this is the part that we can't miss. Like this part here that we're going to talk about. We can't miss whatsoever is coming after this, because these are completely new information, right? And it's going to involve a lot of other things that you must know them. If you don't focus on those things, if you're going to exam see these questions, you might just may well just walk out of the exam, right? Because you have to understand these things that's coming next. Heat transfer, right? I mean, we know that heat transfer from a region of a hotter region to a cooler region, right? So it says that as an object gets hotter, right, there is a transfer of energy, which is obviously heat, moving from a region of higher or hotter region to a cooler region, right? And of course, if this is the hotter region, all right, let's imagine that you have this block right here that is heated, good, and you connect another piece of conductor, such as a piece of metal in between here, right? What you're essentially going to see is that the heat energy, right, is going to move obviously from a higher region, passes through this metal, which has an area of A, right, and pretty much move to the next end. Now, obviously, this heat is going to take some time to travel, so we have to consider what we're going to look at next is going to involve something that talks about how do we actually measure heat transfer, right? And you want to also note the time that the the heat would have traveled from one end to the other end. So all of what you're seeing here, these parameters, they're going to become useful to us in the next slide when we look at a particular equation, right? This thing that we see here about the thermal conductivity. So each material have what we call thermal conductivity, and that just speaks to how easily can this material conduct, right? So when you check out a piece of rubber versus a piece of metal, one is going to have a much higher thermal conductivity than the other. The one that has a higher thermal conductivity means that it is more able to heat up much quicker than the other one, right? So we're going to look at a particular equation, but we just want to lay out these things right here, and we must know how to define what we call heat transfer, the rate of heat transfer rather. Now, the rate of heat transfer is the amount of energy transferred per unit time. So when you heat up that piece of conductor that I showed you a while ago, right? You obviously going to need to note several things, right? You're going to need to note the cross-sectional area because that affects the rate of flow of heat. Good. You also need to know the thermal conductivity because that also affects the rate of flow of heat. You're obviously going to need the temperature that is being changed. So you start out with a particular temperature. What is going to be the temperature at the other end? Then obviously you need to know the thickness of the material because that also can affect the rate of flow of heat. Now, as it pertains to what we call the temperature difference, we generally say that theta 1 is the hotter temperature and that theta 2 is the cooler temperature, right? That for this we're going to use that. Other textbooks can state other things to say that theta 2 is the final temperature and theta 1 is the initial temperature, but for us we're saying that theta 1 is the initial, pretty much the initial temperature, and of course it's going to be the higher temperature, right, in this regard, because remember, if you're doing heat transfer, you're transferring the heat from a hotter region to a cooler region, right? Now all of this what we're saying here, we're going to put it in a formula, right? We're going to put it in a formula, and this is the rate of heat transfer formula that we must know, right? We must be able to can remember it, right? And to be able to can utilize it as well. So this is what is happening here. So Q is what we use to represent heat, and we're dividing that by time. So this makes what we call the rate of heat transfer. Now, if we remember anything about power, right? Power is equal to energy divided by time. So right now, because Q is energy and T is time, the rate of heat transfer is actually talking about the power, right? But we just use the rate of heat transfer because we don't want to mix up the terminologies for power, because power can be used to represent so many things. But this is what it really is. So at the end of the day, when we finish calculate this thing, right, the unit obviously is going to be in watts, right, because of the fact that energy is in joules and time is in seconds, so that ends up being watts. All right. Now let's look at this now, because what we have to understand is that our rate of heat transfer, right, is going to be directly proportional to the area of the material. So if the area of the material is much bigger, right, then it will allow, or what would I say? It's going to take a much longer time, right, for the heat to travel through it, right? Because they're directly proportional. So I mean, you would expect that if the area is much larger, then your rate of heat transfer is going to be much higher, right? I hope I'm saying it correct, because I don't want to say that. Let me see here. if the rate of heat transfer is higher, would that say that it takes a much longer time, or would it say that it takes a much shorter time? I pose a question to you, right? I need your help with that. If our rate of heat transfer is a much larger value because of the fact that the area is much larger, right? Does that tells us that the heat transfer is going to take a much longer time, or it's going to take a much shorter time? What do you think?
Shorter times there.
Shorter time? Okay. Yes. All right. Anybody else want to butt in on that? Let me check the group. Shorter time. All right. Yeah. Shorter time. Okay. Yes. Yes. So yeah, we're gonna work with shorter time, right? It's somewhat tricky sometimes, but yes, let's work with that. Good. And then what we're also going to see as well, depending on the temperature difference, right? The temperature difference here, which is theta 1 minus theta 2, is also directly proportional to the rate of heat transfer, right? So if you have a very large value here, you expect that this value is going to be much higher as well, which means that it's going to take a much shorter time for the heat to be transferred, right? And based on the thickness of the material, which we denote that as X, so X speaks to the thickness of the material. So if that material is very thick, right, that now this is going to be inversely proportional to the to the overall rate of heat transfer. All right. So if that thing is and I think let me just go back here a little bit. Right. So X is the thickness of the material. Right. Mm, so let's see. Um, yeah. So the thicker the thing is, it makes sense. The thicker the material is, right? It's the much slower. Is the much slower? Is it the much slower though that the heat will be transferred into it? But if the area is increasing, then shouldn't it take more time to transfer the heat? Yeah, that's a good question, right? So one of your classmates is saying that if the area is increasing, um, then shouldn't it take more time to transfer the heat? Well, let's think about the thickness though. Like if the thing becomes thicker, right, it's going to take a much longer time. It's going to take a much longer time for the heat to transfer. The area, what the area does, it allows more electrons to can pass through it easily. That's what the area does, you know. So if you make the area becomes much larger, what that does, it allows more free electrons to be able to can pass through it much easily. You understand? Which is then going to pretty much lower the rate of heat transfer. Let me see if you guys get that part. Um, so by increasing the area, you're essentially giving more space for the electrons to pass through to the other side, right? So that would essentially lower the, um, you know, allow the heat transfer to be a much quicker process in a sense. Now, if you increase the thickness of the material, right, that now is going to make it much harder for the the temperature to probably to just pass through easily. You understand? But let me know what you guys think. Yeah. All right. Good. Good. Okay, guys. Another thing we must point out here, because from time to time, if you hear we talking about a temperature gradient, right? The temperature gradient is just the temperature difference divided by the thickness, okay? So if they say to you, find the temperature gradient in a question, right? They're just asking you to find the change in temperature over the thickness of the material. That's what the temperature gradient is. Now, if you want to define the thermal conductivity, as I would have stated earlier, that it is pretty much the ability of the material to conduct heat, all right? And if you have a much higher K value, then it means that it is much easier for that material to conduct heat, all right? And we say that A is our cross-sectional area, all right? Yeah. Let's see here, all right. Hope you guys are taking note of that equation because we will use it eventually. Yeah, guys. When it comes on, I've seen possible questions that are asking questions related to this, so it's important that we understand the concept. All right, I'm going to the next slide. So, in some of your textbooks, you will see this formula from time to time, right? It's no different from the one that we looked at just now. What we're essentially doing here is that we kind of just restructure it in a sense, because what we generally remember, one time we have find the temperature difference. Cool. Temperature difference really supposed to be the final minus the initial. Cool. Now remember, now for this rate of heat transfer, your initial temperature is a higher temperature, right? So in order to fix this equation, if we're going to say that we're using the temperature difference, right? Temperature difference. And in truth and fact, the temperature difference is supposed to be final or initial minus final, which is essentially saying Q2 minus Q1. Q1 is your initial, Q2 is your final. Now, when you do this, when you put this in this formula, right? Or let's go here. Q divided by T is equal to K times A times our temperature difference, which is Q2 minus Q1 divided by X. When we do this calculation, we are going to get a negative number, because if our initial temperature was 100, right, and our final temperature is now 50, we're going to get a negative number. So to compensate for that, we just incorporate a minus sign in front here, which is essentially going to make the rate of heat transfer be a positive value, right? So some books you will see this formula in the book, right? But to just sort of explain it is to just tell you that the temperature difference is because of the temperature difference. The temperature difference is going to be a negative value, right? And to just make the rate of heat transfer become positive, you just put that minus sign in front of it. But if you initially write it as such, to say Q divided by T is equal to K times A times Q1 minus Q2 divided by X, it's not, you don't need to put the minus sign now, because this is already going to be a positive number, right? Because your initial temperature, which is a higher value, let's say 100, minus your lower value, which is probably going to be 50. When you do the subtraction, you're not going to get a negative number, right? So if you want to use any one of these, you can, right? If you see any one of them, don't be confused if you see the minus sign. You just need to know what is your initial and what is your final temperature, and from there you just subtract them and get your values that you need to get. Right? All right. When it comes on to these graphs, right? We need to pay attention to it in a sense. Um, so this graph here is related to what we call the temperature gradient, right? So from time to time, you can actually get a graph like this to figure out certain information and all of that, right? And this is for when we're dealing with one type of material. So if I want to find the temperature gradient of an insulator for argument's sake, then I would expect that as the thickness of the material or as the length of the material increases, right? Then that no, I would expect that the temperature is going to decrease. You know, just the same, right? So it's an inversely proportional relationship going on here. Not inverse, my bad. I don't want to say that. But what is essentially happening is that the more length or the further away the heat is traveling, you would expect that the temperature is going to decrease to a certain amount until it reaches the end that you're measuring the temperature with. So this is just how a regular temperature gradient graph looks like, right? And this is obviously for one piece of conductor, right? Some temperature gradients. Yeah. All right. Let me know if I can change the slide. Yeah. So let's try a simple question for ourselves, right? Take down this question, attempt it, and see if we can calculate the uh, rate of heat flow, which is the same thing as the rate of heat transfer. Do that for me. And as I said, when it comes down to formulas, you have to know the formulas. You have to know when to apply the formulas, right? If you fail to know the formula, then that will eat your supper. So um, try your very best to remember the formulas and to know what each symbol represent. So go ahead and do that for me, please. State on the question. When you're through with that, just send me the answer in the chat. And I think I would have to restart this eventually, because I have about a minute left. So I'm going to restart it now because I have about a minute left and pick up from here. Yes, waiting to see the answers, guys. So once you fix that, you're good to go as it pertains to the answer. So as I was saying a while ago, that some of you can pass your exams only if you just follow instructions and to pay attention to small details, right? So guess what now? This message is not really for you guys mainly as yet, but it says breaking news: CXC makes major adjustment for all exams due to COVID-19 and the St. Vincent volcanic eruption, right? So you guys might get away a little bit this year again. Yes, Rihanna, answer is correct. Wait, I'm not sure what you're not doing correctly, right? You have the correct values per se, but something is mixing up you somewhere along the side, somewhere, right? You're supposed to get 62.5. So see what you did wrong again. So yeah, we just did this a while ago, but hopefully, you know, why don't I got the on the side, in a sense. I don't know, but CXC has made some adjustments again, I think. So let's see what those adjustments are. Let me hope that this message is um, really news. We still don't know what kind of changes they might make as well. All right, we realize the rest of students them not answer the question. We not get the answers from them. Only a few students submitting the answers. Boy, Pakistan, I don't know how you get that still, I don't know how you get that, bro. Albert, you try the question, Albert?
Repeat, sir.
You try the question, sir?
Ma deal with it now, sir.
No, you take too long, Bridget. You take too long. Who else out there now? Let me see. Realize that the population of the class decreased. Erin, what the answer, Erin?
Hold on, sir.
Baker, what the answer, man? Guys, you all need to be firing up now, when it comes out to calculating stuff, you have to be firing up now. Teresa, I didn't see your answer yet. What happened? Let me check the chat and see what's going on over here. All right, good win. I'm happy that you got the answer now. Amanda, let me see. What did you say first? Yes, Amanda. Yeah, man. You answer correct, man. Jesus, baby, God. But on a serious level, still, that yes, Kerry, I need the answer. I need the answer. That's what I want. Thank you. But what's the unit? Remember, you see that's another thing with you guys sometimes, no, it's not that. I told you what the unit was. Yes, Erin, that's the answer. The unit is watts. The unit is watts. All right. Yeah, I'm gonna move on. Albert, you got the answer yet, Brethren?
No, sir. No.
Tell me what you do. Tell me what you do so I can help you. Talk to me
Sir,
about.
it goes, sir.
Eh?
It goes, sir. Go.
No, bad man, don't tell me
Go,
that, man.
sir. It governs.
Yo. Don't tell me that, man. You don't want to hear that. Why you walk me through what you do? That what you do. You understand? So tell me where to start off, Bridget.
Sir, repeat.
Tell me where to start off. Tell me where you're starting off from.
I have the understanding the change the Q thing. I understand that part.
Tell me what to write. Tell me what to
Like
write.
the other side
Tell me what to write. That what you do.
tell you what.
Yeah.
Oh, changing Q over changing T.
Alright, yeah, we can work with that.
Equal the thermal conductivity of wood.
Of food.
And
You hungry, Bridget?
wood.
Oh.
No, sir. Wood, sir. Wood.
Alright. Yeah, what else?
Multiply by A. Multiply by the change in T.
Alright, it's a change in T, but how you gonna write? How you gonna write it?
Change.
So yes?
The triangle, sir, with the T beside it.
Yeah, I know, but when you say change
Over.
What?
Over the change in X.
Alright, X. Now, when you say change in T, what does that really equal to? That I want you to tell me that. What is that equal to?
That's the temperature, the change in the temperature over time.
No man, this is the temperature difference. How can I write out the temperature difference? No. What would I write here for the temperature difference?
Oh. I don't know that part. I don't understand that, sir.
Q1 minus Q2. Or theta 1 minus theta 2. You follow me? That's the temperature difference. So all you just need to do now is to go ahead. You get the thermal conductivity of the material, which is 0.1. Now the question gave us all information of the door, right? It gave us the height of the door, or and it gave us the width of the door. So if you got the height and you got the width, then it means to say you can find the area. You understand? So the height is 2.5 and the width is 1 meter. So you can find the area of the door. They gave you the thickness of the door, which is your X value. That is going to be used down here. So the area in this case is going to be 2.5 because 2.5 times 1 is going to give you 2.5 meter squared. And you're going to multiply that now by your change in temperature, which essentially is going to be the higher temperature, which is not Q, but 35 minus 25. Divide that now by this thickness, which is in centimeters. We have to convert that over into, obviously, meters, right? So this is what's going on. Oh, so this is what you're going to do now. Divide that by 4 times 10 to the minus 2 meters. So when we do the maths now.
So after write like that, sir, times 10 to the negative.
You can write it as 0.04. But for me, this is the easiest way of converting into centimeters. Because what I see sometimes, you guys try to convert it into decimals and you still make some errors. So for me, I just simply just say, all right, centimeters times 10 to the minus 2. So all I need to do is to incorporate that into my calculation. You have to try to make life easier for yourself, you know. Right?
Yes, sir.
Yes, Patrice, I know that your answer was incorrect at first. So yeah, it's good that you got the answer now. So when you do the math now, right, you're supposed to be then
Yes, sir.
getting some value to say that, you know, your change in, you know, the rate of change in of heat transfer, right, is equal to 62 watts, right? 62 watts. If you work out this, you're supposed to get that. I really left the thing this still, you know.
Thanks, sir.
Yeah, man. All right. Now we're gonna move on to something else. Well, not to something else, but it's going to be a little bit more addition in a sense to what we are now learning. And it is when we have different materials, because from time to time you will connect different materials together. And with that being said, we can now find the overall you know, well, not the overall, but sometimes we do this to find maybe the thermal conductivity of one particular material, right? But what you have to understand is that the rate of heat transfer through one material is going to be equal to the rate of heat transfer through the second material. So here I have metal C and I have metal D. Whatsoever heat that is going to be transferred from temperature 1, right, to temperature 3, well, not a temperature 3, but let me say that again. So essentially, let's imagine that T1, right, has a temperature of, say, you know, maybe 100 degrees, right? What we're saying here is that heat energy is going to be transferred. The rate of heat energy is going to be constant for both materials. So whatsoever heat energy is transferred to material C is going to be equal to the rate of heat transfer through the second material. That's just how it is, right? But there's an important point that we must understand is that when the heat transfer completely through material C, right, there's going to be a temperature, which is what we're going to call it our we can call it our equilibrium temperature in a sense, because what you're going to see happening is that this temperature T3 is going to be the temperature that the second material is going to start out with, right? So that is sort of like what we call the almost like the equilibrium temperature, because that is the temperature that both materials are essentially going to have. You understand? The temperature at that point is not going to be different, right? So whatsoever temperature is at the end of the material, the next piece of material are going to have the same temperature, right? So that's something we just have to know. And I think we understand that T1 is obviously going to be greater than T3, and T3 is obviously going to be greater than T2 because it's moving down a temperature gradient, all right? Now for this example here, the areas are pretty much the same, right? Go ahead.
Could you go over about the temperatures again?
Which part do you want me to say again? About the temperature being greater than and whatever?
There's a T1, T3.
Okay. Yes, so the temperatures, right? Remember, it's a temperature gradient. So what you're essentially going to see is that T1 is obviously going to be a higher temperature, right? So when by the time you reach T3, that temperature is obviously going to be less than T1, obviously. And when you reach T2, that temperature is obviously going to be less than T3, right? As you can see right here, right? This is just explaining what is happening with the temperatures, right? But you must be mindful that the temperature that is right here in material C is going to be the initial temperature for material D. So the final temperature in material C is going to become the initial temperature in material D. All right? And because we said that because the materials are joined, right, that heat transfer is equal to each other. So the heat transfer in material C is automatically equal to the heat transfer in material D. And for that reason, we can equate them using the formula, right? So as you're seeing on the screen here, we're saying that the rate of heat transfer, right, in material C is equal to the rate of heat transfer in material D. And then we can just rewrite it as such to say that the thermal conductivity of material C times the area times the temperature gradient is equal to the thermal conductivity of material D times the area of material D times the temperature gradient for material D. Now, remember, we're saying that the areas are constant as well, right? So in most cases, the areas are constant, right? And you'll see that eventually when we try a few examples, hopefully I do have examples. But what I need to highlight in this regard is the whole thing about the temperature gradient, because this one can be a little bit tricky, right? So imagine that I'm plotting a graph for my temperature gradient. Obviously on this side is going to be my temperature, right? And this side is going to be my X, which is talking about the thickness for the most part, or the length per se. So what you would see, this is going to be T1 on this side, and T1 is going to have a temperature gradient as such. So this temperature now is going to be T3, right? And from here to here, let me use a different color. From here to here, this is going to be the thickness of material C, right? And then for the next material now, so remember we said that this is T3, cool? Then the next temperature gradient, it looks, let me just kind of make that a bit different, because give me a second. There has to be a little bit of a distinct thing about it, that these are actual change. So let's just cut it down like that, right? So right here would be T2 corresponding right here, and then now from here to here would be that that XD, which is the thickness of the material, right? So this is how you would draw the temperature difference graph for when you have two different materials, right? I'm going to see if I can find a different graph to show you what I mean mainly, but this is what it generally looks like if you're dealing with two different materials, all right? But let me know if you guys follow what I'm saying here, because the materials are joined together, you have to connect the temperature difference on the same graph, right? And this is how we generally go about doing it, where you would obviously have the first temperature gradient for the first material, and then you're obviously going to have a final temperature that is going to be met at. That final temperature is going to be the initial temperature for that next material, and so you would start the next portion of the graph behind it, right? And obviously on the x-axis, right, that region that is below it right here, right, speaks to the thickness of the material. So whatsoever the thickness of the material, so the thickness of the material is 10 centimeters, then all are down here so must be representing 10 centimeters. If the thickness of the material for material C is 20, all of what is below here must be 20, right? So that is just what is taking place here. But let me see if I can find a diagram to just show you quickly. aluminum is 200. All right, so we said that steel is 40 in terms of the K value, and for aluminum, that's 200. Okay, so we have that now.
Sure, we didn't get a value for A.
No man, A is constant, See, so because A is constant, let's write out the equation. So, so this is for the rate of heat transfer for aluminum. This is going to be K times AL, right, times the area, which is the area of the aluminum, times the temperature difference, which is, theta 1 minus theta 2 divided by x, right? And that is equal to K, this is for what? Steel. So K steel, so the thermal conductivity for steel, right, times the area for steel times the by the way, theta 2 is what we're trying to find, so that is now going to become my initial temperature here. So you'll put theta 2 right here minus theta 3. We can write it like that. We could have done it differently. We could have called this theta 2 actually theta 3 because it's in the middle, right? And then call the other one theta 2, but we don't have to worry about that, right? As long as we're trying to find the right thing. Cool. And then now we divide that by the x value, which is the thickness. So let's look at the question, right? They have it to say that the thing have the same area. If they have the same area, it means to say that the areas are going to cancel out here. We can cancel them out. Cool. And then now we have all the values now that we really need. We just now need to put things together per se. You think you can do that?
Yes, sir.
All right, good. Yeah, Father. Still I stay strong. Still I stay strong. Right now, the priest say, couple on the well and submit the book on now. But me not say a word. You think me I say a word? I have about 16 or so books for you guys, or at least 16 thereabouts. I know it's not above 20, so at least half of the class still not submit them book yet. But me still a stay strong. Still a stay strong. Yeah, you have reason, but me don't know your reason. Yeah, your reason, me don't know it. You can send it to the bus driver. I know bus a travel from Trelawney. But either way, are we getting any answers so far? All right, cool, cool. Yeah. Yeah, bro, you just need to do what you have to do, you know. You understand? Make sure to make it my thing, you understand? That's all me want in the bridging. At the end of the day, me no want DC bother me about anything. You understand? So me need to get everything what me need to get from Uno. Right? So when Uno no submit no who you think are getting in trouble, who you think are go not to get in trouble, but who you think are go in a problem. Right? I don't know, somehow when they send one work, me look on it and see what I go on with the lab. Oh boy. Alright. We get an answer yet? Alright. Good, Nugent. I think that's the answer for real, yeah. Well done. Well done, good and faithful servant. You know, I hope that's what we all will hear when the Almighty returns, you know. Well done, good and faithful servant. Alright. Alright, so make a pre-walk one now. Alia, I'm not hearing from you from the end, Alia. What am you in our class? I want to know not asking for a recommendation, Jason, when I got university, you see. I want to know not asking for a recommendation. And so me go right on here. You better not make that happen here. Plumber. I see your answer, Plumber. I see your answer. Right? See your answer. But I don't understand. Alia, Wam, you in our classes or no? 31 class, I don't say, I don't participate. Me no. See, me have got decline your recommendation, because it's a true word, you understand, out in the public domain. So if it catch you, then it catch you, right? Me true me stone, me never call no foul, right? So, all right, I think I'm just gonna just take this and bring it over here. Should I do that? All right, we don't have to do that, but let me just see here. Um, 200 divided by 30 e to the minus 2. Let me hope that this makes sense. I don't like um, the amount of decimals I'm getting already, but let me see the easiest way to do this. All right, either way, we're gonna try it same way. What I'm about to do is to just expand this. So we're going to take this number from that is on the outside and multiply it throughout. So when I do that, I'm essentially saying 667 times 250, I get 166,750 minus 667 Q2 is equal to 80 Q2 minus 8, well, 80 times 100, That's 8,000. Right, let's see if this makes sense to us. All right, I see your answer, Amanda. Let me just see now. I don't know if this makes sense, but I'm just trying it. We're going to group the things together. So I'm going to take this from here and bring it across the equal sign. And I'm going to do the same thing for this. I'm going to bring it across the equal sign. So when I do that, I'm essentially saying 166,750 plus 8,000 is equal to 80 Q2 plus 6,000, not 6,000, 667 Q2. So let me do the maths now. So 80 plus 166,750. I got 174,705. That is now equal to 800. Well, not 800. 80 by the way. 80 plus 667. That is 747 Q2. Let's divide it and hopefully we get the answer. I don't know. Let's try. So 174,750 divide by the answer. All right. So yeah, this is the answer. Right. So theta 2 is equal to 233.9 degrees Celsius. All right. That's the answer. Any questions? I know a few persons got the answer. Right. For those who didn't get the answer, just look back and see where you went wrong. You can also comment to tell me where you went wrong as well, just so I can know. Sir, okay, cool. Yeah, man, welcome to the world, Welcome to that world where, you see things that go crazy. You haven't seen nothing as yet, right? When we start talking about the kinetic gas theory, or kinetic gas and the whole kinetic theory and all that, that's where you're gonna see some crazy stuff happening. I had the correct answer, right? Well, I had the right side on the left side, sir, and the numbers switched up. Okay. So yeah, you have to kind of pay attention, because if you write the wrong thing on the wrong side, then it'll throw you off, But yeah. So the length for the wire, well, for the bar, for the aluminum is 30 centimeters. So you have to keep that with the overall temperature, or the temperature difference for the aluminum bar. You can't mix up those. If you mix them up, it'll throw off your answer, right? So thumbs up to those who got the answer. Anybody here don't understand what we just did as it pertains to this? All right. So I guess we can move on then. Oh, we're supposed to draw this up, We're supposed to draw the graph. So let me just rub out some of this and make space for that. All right. So now that we know the final temperature, which is about 234, then we can actually draw the graph now. So let's see if we can go ahead and do that. So at all times we know temperature goes on this axis. Now we started out with 250, so 250 goes here. Then we would have fallen to 100 at some point. That would have basically be the final temperature. Now in between, now this is going to be where about 234 might be right here. So when I draw my graph, by the way, I need to put in the thing here. So I'm going up by 10. Let's imagine we're going up by 10. So 10, 20, 30 centimeters will be here, and then possibly 50 centimeters will be here. So this is how the graph should look like. Then now the next part now, I'm wondering if I'm doing it correctly, because it's supposed to, there's supposed to be like a distinct change in it. I'm not sure. Maybe if we actually put it on a literal graph, we'll see the actual change. But for my one, it looks a little bit weird, but it looks a little bit shaky. But you should see the distinct change in the temperature gradient though, right? So just ensure that if you're drawing it, you're supposed to see a distinct change, right? Like you must see that the thing actually bend in a certain way, right? I think this line looks more like it in a sense. For argument's sake, it looks a little bit much better, where you can see a distinct change and all of that, right? But it's up to you how you want to draw it at the end of the day, right? It's no rocket science. Okay, so that is that, right? Let's see another question. Let's see what time is it. All right, we have time. All right, let me see what this is asking us now. We want to determine the amount of energy lost. All right, cool. What is this related to now? Oh, it's a different. Okay, this is not related to the previous one. This is just overall a general heat transfer question, right? What they want us to find here is pretty much the amount of heat that was lost through the glass over a period of 5 hours. So you can read the question and see what it's saying here. It says that an inner and outer surface of a 0.5 centimeters thick 2 meter by 2 meter window glass in winter are 10 degrees Celsius and 3 degrees Celsius respectively. Now it says that if the thermal conductivity of glass is 0.78 watts per meter, right? It says determine the amount of heat lost through the glass, right, over a period of 5 hours, and then it then asks us to say, what would your answer be if the glass was 1 centimeter thick, right? So if you are one student who plans to go into like certain engineering field where you're designing houses and so forth, now this thing here comes in a little bit handy, where you would essentially could essentially calculate, how much heat is being lost through a particular window or any material that is used to make up the house. And so for somebody who's going to build a house like maybe in England or some other places, you want to ensure that the material that you're using, right, does not allow a lot of heat to be able to can escape, because you have your heater in the house on, you don't want to know if you lose heat in the winter. You understand? So, I mean, these are stuff that applies in that regard, you know. So you can go ahead, try this for yourself. Nothing hard, nothing too easy at the same time, and then let me know what you guys are coming up with. Still I stay strong. I'm pretty sure some people now come to class like one time again, but sorry for them. Gabriel Woodburn.
Yes, sir.
When I see you submit no answer all now, you know. None of the questions I'm sending you. You have to make a formal report or a formal complaint.
No, sir.
Oh, really? Can't hear the TV now in the background too. So just call Miss Woodburn right now and tell her the day I watch TV. And then at the end of the day, teachers get the blame. Hmm? Sometimes, you know. It's your breath in our lungs, so we pour out a praise. Ali, you don't have to be jealous in Alia, you understand? You don't have to be jealous. Brown dog, that's much energy you get? What, you might be right still. Let me see some more answers coming in. I don't remember My working out for that one. I think I have the working out. Let me just check again. Which question that? No, partisan. That can a little bit too much. We don't know. We don't know. Let me just check something quickly. Let me just verify something. My bad. Let me just check something. Yeah, you're right. You're right. You're right. You're right. You're right, dude. You're right. I swear I was looking at. You're right. You're right. Let me see some more answers now. I want some more answers. Come on, guys. So I want some other big question. I don't understand. I see your answer, Kerry. I see your answer. I see your answer, Rihanna. Um, yeah, you're right to say that, Kerry. Make the corrections to that. Yeah, it is. It is. Yes, Rihanna. It's correct. Yeah. Good. Congrats to those who got the correct answer. Wind. I'm gonna see your answer it, Wind. What happened to you?
I'm almost finished.
Okay. Erin, you're working it?
Yes, sir.
So you're afraid of embarrassing yourself in Alia. Okay, good. So Alia is saying that before I embarrass myself, it's a very big number, like 10 figures.
Sir, that's not the purpose of the chat. That was on mute and ask.
I mean, you should have told me, sir, don't read it out loud, then I wouldn't have done that. But there wasn't any um, limit to what I could do from what I couldn't do. It's actually a lot of figures, right? It's a very large number. So your answer could be right. If you just give me the number, then I say, all right, yeah, you could be right. And as a matter of fact, you're giving it to me in the chat, so you know. So yes, that's the answer, Alia. Like, I mean, with you know, with you losing probably a half mark because you don't have the unit on, right? Yeah, yeah, Albert, that wrong, man. That wrong, brother. Well, let's see what I go on this now. So clearly, Q upon T is equal to K times A times, Q1 minus Q2 divided by X, right? So one of the easiest things to do is to just transpose and make Q become the subject because it's Q that we want to find, right? So the best thing is to do is to just make Q become the subject. So Q is equal to K, which is 0.78 times the area which is going to be 4, right? Times that change in temperature, which is going to be 10 minus 3. Divide that by thickness, which is 0.5 times 10 to the minus 2, and then we're multiplying that by the time. The time is 5 hours. No, guys, in 1 minute there is 60 seconds. In 1 hour there is 60 minutes. I need to know how much seconds is in 1 minute because I have to make my calculations in the SI unit. So at all times you have to be ensuring that your calculations are in the SI unit. So at the end of the day, 1 hour in terms of seconds is equal to 60 times 60 seconds, because 1 minute is equal to 60 seconds. So 1 hour is 3,600 seconds. So if I have 5 hours, it means that 5 times 3,600 seconds. Cool? So at the end of the day, when you do work out all of this, right? We can work out. Let's just do it for the fun. So 0.78 times 4 times 7 times 5 times 3,600. So the numerator is this, and then I'm dividing that now by 0.5 times 10 to the minus 2. Let me hope that I get the answer. 0.5 e to the minus 2. Yeah. So when I do that, I get my energy that is lost, which is, this amount of money I would like. 78,624,000 right here, and obviously it's in joules. So that's the shortcut of doing it. You could have found the rate of heat transfer first, then you could have gone ahead to find the the answer to just, so what you could do is to say that because you know that power is equal to energy divided by time, because that is what the rate of heat transfer really is, right? The rate of heat transfer is just talking about the power. Good. And having said that, you would have calculated the rate of heat transfer using this information here. Then you could have equate that to equal to the power and then transpose to find energy. But the easiest thing to do, given that you know the time already, you could just put that into the working out and find Q. So, you know, that is really what we're asked to do right there. Now, I don't know why this class seems so long. Like, you know, it's really long. I know it's coming to an end, but it seemed really long today. All right. You see, the next thing that we're going to move on to next class, right? Is going to involve. I can't believe tomorrow is Friday already. Rock, stone, right? But all of it are still PA day is coming up soon, so you know what I mean. I don't mind that, right? But when we look at this whole thing here, the syllabus asks us to discuss it, right? So we're going to look at the whole this whole method of determining the thermal conductivity, right? And I think we are almost, well, no, we're not there as yet. Like, we're nowhere close to finishing, because this is just talking about conductors on a whole, right? We haven't touched the whole aspect of thermal convection as yet. And after thermal convection, we'll go into thermal radiation, which speaks to some other calculations that we have to do, talking about Stefan's law and all of that, right? So we have a far way to go, because we have to discuss even greenhouse effect and global warming in a sense, right? And then now talk about the application of you know, conduction, convection, and radiation. But I believe by tomorrow we can finish this up still, hopefully, God's willing, right? So that's about it for today, guys, right? If you have any questions, go ahead and ask the questions now.